So good morning, everybody. We are going to start our CMCC webinar. I have the pleasure today to moderate this talk by Luigi Vidale, and we are going to talk about the future evidence of the value of resolution and its surrogates in general circulation model simulation of tropical cyclones. The idea is to give you a brief introduction of what CMCC is, what we do, and then I will leave the floor to Luigi for this really exciting talk. First of all, what do we do at CMCC? We are a scientific institution, we are a research center, and our main objective is to model the climate system, just to investigate climate variability and change, and also to investigate the predictability at different time horizon. The idea is also to develop foresight and quantitative analysis of our future planet and society to inform stakeholders and policymakers. The institute is mainly distributed through three different institutes: the Institute for Earth System Prediction, the Institute for Climate Resilience, and the European Institute of Economics and the Environment. Within each of these institutions, we have the different research division of CMCC, and we mainly, as I said, we mainly build on our modeling capabilities, and with this aim, we also have a supercomputing center in Lecce. Here you can see a few specifications of our computing center, and many people working in the different division at CMCC in different places around Italy uses our supercomputer for our objectives. So as you can see here, there are different locations in which CMCC is, and these are mainly consistent with the initial consortium with which we start the CMCC, with different entities, different research institutes and university around Italy. But going to the present talk, there will be at the end a question and answer session. You are supposed to add your questions to the Q&A section, or you can also raise your hand at a certain point. So the idea is to stay within 30-40 minutes for the presentation, and then we will move to the question and answer session. So maybe I already made a mistake. So in the meanwhile, Giovanni, while you give the floor to Luigi, just to let me introduce Luigi Vidale. Professor Luigi Vidale is from Reading University, is professor of atmospheric science at the Reading University, the meteorology department. Please, Luigi, correct me when I'm wrong. And he is also a senior scientist at the NCAS, National Center for Atmospheric Research. Luigi is an expert of climate modeling and extreme event investigation, with a particular focus on the interaction between land and atmosphere. And also, and this is the reason why we asked him to give us this talk on tropical cyclone within general circulation model. Luigi also is the director of the new program that started in 2021 within Met Office, ECNWF, and Reading University, am I right?
And the National Center.
And the National Center for Atmospheric Science, regarding the improvement of our knowledge in terms of Earth system prediction. So this is a long-term program, and we expect that Luigi will comment a bit also on this eventually, and he's also leading different research project related to high resolution. Just to mention a few of them, there is the Huracan one, and many others that probably also you will hear about during this specific talk on tropical cyclone and their representation in general circulation models. So once again, thank you for Luigi for being here with us. This is a really important topic for us at CMCC because, as you know, we are really interested in the relationship between tropical cyclones and the climate system, and what you are showing us is really, really interesting for us. So I leave you the floor. Go ahead.
Thank you, Enrico. Thank you very much for the invite, and it is a pleasure to be here. I wish I could give the talk in Italian, but then probably I wouldn't do such a good job. Been in the UK for far too long. So yes, tropical cyclones, fascinating phenomena, and things that have affected people around the planet for a very long time. So Kerry Emanuel likes to have his art in his books and all that, and I heavily borrow from his sort of philosophy and approach to the problem. So this is one of the many bits of art in Kerry Emanuel's books. And yeah, the name Huracan, I will talk about this project towards the end of the talk. We have a NERC NSF, so UK, US project, all dedicated to hurricane risk in Europe. And you just had an example, a week ago, of hurricane risk in Europe. So just to say a little bit about, so this is the high resolution climate modeling group. Sorry, I should use the pointer, not my finger. So high resolution climate modeling. So this is a Met Office, NCAS. So Exeter is Malcolm Roberts and my group in Reading. We've been collaborating for 20 years. And we have a bit of a somewhat alternative philosophy about the use of models. So first of all, this idea of using models to interpret, challenge, and complement observation. So this bit about challenge comes from my PhD, when I was in a huge field campaign and my model results was saying that the way that the experiment was designed was wrong. I was in my first year as a PhD student, and of course I was nearly killed by the PIs, but it turns out I was right. And in fact, sometimes theory can help, and the models sometimes can reveal a bit of theory. And this idea of complementary observations, and I think this idea of complementary observations is a very powerful one. We were talking with Enrico about using models to build data sets we can also use to study the climate system. And I will give you an example, and you can see already there is a hint of what I'm talking about. Challenge the databases. The models are wrong, but they are consistent. So, and they are physics based, and they can tell us about where to go and observe, where to go and try to understand better. So just to say, for a long time, so we've been working together for 20 years. So it's always, what is the role of these unresolved processes? And now we are at the mesoscale gamma in terms of unresolved processes, phenomena, and all that. What is their role in the climate system? So in many ways, we're about upscaling. We're doing the opposite of what a lot of people do, which is downscaling. We want to understand what the combination of all these processes of these very fine scales does to the rest of the climate system. So in particular, we are looking at organizing propagating convection, and you could think of these beasts are as macro examples of organized propagating convection. And then, yes, there are people in the group, particularly the people that work with the sub 10 kilometer models that are looking at clouds, and Malcolm and others are looking at ocean eddies. Nowadays, the models have this capability. They are eddy rich, not quite eddy resolving, but they're eddy rich. And again, what is the mixing? What do they do to the rest? What do they do to transports, particularly in the ocean? And yes, in the end, do they do something? And then maybe through teleconnections. And we had an early example. One of Malcolm's early papers had to do with what the mesoscale was doing in the tropical Pacific, and how this mesoscale was contributing the mean state that then allowed ENSO to form with the right frequency. So if we didn't have this correct mean state, that was not possible. So that was one of the papers from EERIE simulator. So this is a diagram we put together for EERIE, this new project where we run everything at 10 kilometers in the ocean and 10 kilometers in the atmosphere. And the idea is exactly to study these processes and then to understand things like transports and boundary currents and all that. And then eventually to understand the connections and to understand the future projections in the context of perhaps better simulated internal variability and better simulated teleconnections around the globe, and understanding these relative risks. So that's the philosophy. Right, let's go to tropical cyclones. So in many ways, well, yes, they are fascinating phenomena, but for us, particularly as model developers, what we are doing in so many ways is much more justified by tropical cyclones than it is justified by attempting to study global temperature. So this is the famous Hawkins and Sutton diagram. It gives you the lead time in climate prediction. This is for global temperature, and it tells you about the relative weight of interannual variability and scenario uncertainty and anything else that you could consider to be model uncertainty. So global temperature is very heavily dominated by, as you go to long lead times, by the uncertain scenarios. If you go to regional projections of temperature, this model uncertainty starts to be more important because the models have the wrong regional distribution of phenomena like storm tracks and all that, and transports, and the relative roles of the hydrological cycle on the ocean, hydrological cycle on land. And so this model structural uncertainty is heavier. And if you look at now projecting hurricane frequency, this is something that Benoit Vanier did a long time ago, and you look at the relative importance for the northern hemisphere of the scenarios, it's almost nothing. The reason being that the model uncertainty is so huge. And just for the North Atlantic, oops, there is a H missing, still scenario uncertainty, maybe the interannual variability starts to become more and more important. So just to say that if you're studying something very particular and if you're studying something that affects regional risks, I see a lot of obsession with scenarios, but the model uncertainty and the disagreement among models is still very, very important. So this is one of the reasons why we insist on investing in models and understanding the physics. So yes, we have known for a long time. So we had this special working group on hurricanes as part of US CLIVAR program. Enrico was part of it. It was a long time ago. And a few nice things came up. What we know already, that as we increase the resolution, we start to see these are tropical cyclone storm tracks and their density. So this is storm transits per month. And so here we have the official data set, the official catalog. This is IB tracks. And we have some reanalysis. So this is one example of one reanalysis. So extracting the storms from a reanalysis, then forming these so-called track densities. And we have a number of models that we ran in Primavera HighResMIP at around 20 kilometers. You see that most of them have a realistic distribution. So as we go towards 20 kilometers, we see the means starting to look, except for perhaps that model that calls high resolution something that we would consider to be coarse resolution. But in general, we know that as we go to those resolutions, we resolve something that looks like a tropical cyclone. This is a very nice example of the skill in reproducing the interannual variability of a number of tropical cyclones in the North Atlantic. I think this is the gold standard for interannual variability. This is Ming Zhao of 2009. That's a remarkable result. So he really could represent all the way to the famous year 2005 when we had 14 really important hurricanes, and their model could do that. And we're at the same time that Ming Zhao was publishing this, we were writing a proposal to use PRACE, and we ran our model at multiple resolutions from 135 all the way to 25 kilometers. We had 5 ensemble members in each, and we showed that we had the same result, and many other groups have done that. So it's not just the means that are improved by resolution, but also this response to the environment. And so what is the risk this year versus last year versus perhaps future year? So we've known that for a long time. What we also know is that, yes, we're doing a good job, but what we simulate has the shape or the morphology of a tropical cyclone, but is in fact probably too large and too bland. And so this is an example of results from Primavera. So this is the maximum lifetime 10-meter wind speed on the x-axis. I've lost, oh yes, it's come back. And this is the minimum MSLP. So this is the so-called wind pressure relationship. In black are the observations, and these numbers here you see on the 2 axes 1 through 5 are the categories. So you have the categories in terms of 10-meter wind speed, and you have the categories in terms of pressure. So this is what we should be doing. This is what has been observed, taking the storms from the official catalog. And these are all the Primavera models, and every time you see a model pair, you see it as a continuous line, and then you see a dashed line is the low resolution model versus the high resolution model. So most of these models, as we increase the resolution, try to go toward observations in terms of this really important pressure-wind relationship, but they don't quite get there, except for this French model. So at 20 kilometers, the French model at the time was reproducing the distribution. And this is a very, very nice example of the right results for the wrong reasons. We should not have at 25 kilometers. So Bill Gray, who was my teacher, so at Colorado State, almost every week he would come to us in the classroom and say, "You people," he meant the modelers, "always have the right results for the wrong reasons." And so this is a very effective. So he hammered this in my brain. And this is an example. We should not. There is a very nice paper from Chris Davis from a few years ago. But there are 2 ways to look at it. So he took Katrina and basically transformed Katrina into what a model would reproduce at different resolutions. And it shows you that at these resolutions, we should not be simulating the full structure. So the size and the intensity and the pressure distribution that you see in Katrina. So he's got these plots, what Katrina should look like at 7.5 nautical miles all the way to 60 nautical miles. And so this is the wrong result. We shouldn't be doing that. And we have some ideas how it was achieved, but it was achieved through some sort of tuning of the surface layer, and then probably messes up everything else in the current system. So if you want to use the whole global model to reproduce hurricanes, fine, but then it means everything else you're doing is probably just wrong. So that's a nice example. So what most of the Primavera models are doing is correct. At that resolution, we should represent mostly category 2, maybe a bit of category 3, and category 4 and 5 mostly are out of scope. Yeah. And yes, as I said, we do. So this is the low resolution GCMs in Primavera, and this is the high resolution. So this is basically, these are composites of the most severe storms. And yes, they do look like tropical cyclones. They have a right structure. If you look at them through the whole of the troposphere, they have the right structure. And yes, we decimate the lower categories as we go to higher resolution, and we start to have a few, but very few of the higher categories. So for some of these models in the whole of the Primavera exercise, we had 1 or 2 of those. So it's a very rare phenomenon. So this we've known. Something else that has come up in Primavera and occupied my attention for 2 or 3 years to try to understand it is, well, the fact that in Primavera, we didn't just have the models run several times at different resolutions. So usually 150, 20, or 100 something, 60, 20. But we also had models that use stochastic physics because other people, and there are people in the Met Office, but also Tim Palmer have been suggesting that stochastic physics is really important, and for NWP it's definitely important. But then Judy Bernier and others have applied all these ideas in climate, and they've shown that stochastic physics is also very important for improving the statistics of tropical precipitation. And so we realized at the time that as we were looking at so this is an example of a tropical cyclone track density from EC-Earth. This is not from the Met Office model. This is from Paolo Davini. So you probably know who Paolo Davini is. So he ran this massive ensemble with EC-Earth at 5 different resolutions. So this is the coarsest resolution all the way to about 16 kilometers without stochastic physics and then with stochastic physics. And we tracked his simulations. So this is a very large ensemble. It's an extraordinary piece of work, what they did in this, it's called Sphinx, this experiment. And we extracted the storms. And what we see at all the resolutions that we got these massive lobes at fairly high latitudes. And also we started to see more and more of this that shouldn't happen according to observations. And I was trying to understand why we have these massive lobes. Also, I realized that, well, actually, systematically, as we go from a model resolution, say 170 kilometers to the same resolution plus stochastic physics, we have more tropical cyclones. And if you take the difference, where we have more is exactly where the tracks are. And if you go through all the resolutions, this is a systematic response of the system. So basically what this says, and you can count them, this is another way to look at it. This is how many there are. So this is the TC frequency per year, starting at the coarsest resolution, plus stochastic physics, next resolution, plus stochastic physics, next resolution. So you can see the stochastic physics is like a half a resolution. And it's really interesting because in a sense, you're just adding noise. So you just add some randomness and you get a tropical cyclone out of it. That's quite magic. That's quite remarkable. But it is also very annoying because it does all sorts of things, particularly to interannual variability that we're still trying to understand. But it is interesting. And it's also quite attractive because if it's like a half a resolution for tropical cyclones, but for many other things, the computational cost is just 5%. And if you just add 50% resolution to a model, just because you have more points and you have a shorter time step, that's a 240% increase in computational cost. So that's quite attractive. It's quite economical. So we're still using stochastic physics in the next project called EERIE. And almost no one would doubt that stochastic physics is beneficial. We just have to understand its effects. And particularly what I'm trying to do now is to understand the effects on interannual variability, because in my paper, I show that actually in terms of interannual variability, it made things worse. So it made the means much better, but it made things worse in terms of interannual variability. But that was only with one model. And it's not clear to me that that applies to all of the Primavera models, at least the ones that have stochastic physics. So I don't have time to talk about that today, but let's go to EERIE. So the successor to Primavera, similar ideas about having a protocol like HighResMIP, a bit more ambitious. So the idea is to start in 1950 and go towards the end of the century, so 150 years. And well, the ocean is central, so the 10-kilometer resolution in the atmosphere is a horrible, horrible thing to do. I offered Dave Randall to take back my diploma because he told us either you stay at 100 or you go to 1. Don't go to anywhere near 10 kilometers, but it's because of the ocean. And the reviewers understood it. It's a compromise because our interest is in what happens in the ocean. I showed this before, what these eddies are doing in the ocean and how this upscales. And there was a hypothesis that interannual variability might be stronger in such an ocean. And in fact, we wrote this and we submitted it. And then this paper from NCAS came out where they show that for an eddy-rich ocean, this sort of decadal variability is stronger. So this is one of the metrics of variability in the model compared to the standard model. And now we're starting to see it in the models that we are running in EERIE. At the same time, there is an opportunity, if we have a 10-kilometer model, to look at what the tropical cyclone look like in a 10-kilometer model, both in atmosphere-only mode, which is what I'll show you next, and then in the coupled system. And just to say, Malcolm, who's a bit of a contrarian, has decided to run 1850 to 2100. So he started a long time ago. He will have a simulation. Initially, it was going to be 1010. Now, for the time being, it's 20 in the atmosphere and 10 in the ocean. But he will have it comparable to a DEC simulation. And then we'll run also 1950 to 2100 in coupled mode. But I'll show you just now. So what I've done in these few years since Primavera, we built the 10-kilometer atmosphere and I've run it as an ensemble. I'm still running the last ensemble member. So I have 5 ensemble members. It's still running. As of last night, I was in 2009. I still have a few years to go, but I'll show you some ensemble members. So the historic period, and then we're doing a 4K plus 4K simulation, and then we're doing another one without deep convective parameterization, and I will do one more without stochastic physics, just to continue to understand this issue of stochastic physics. So revisiting now the pressure-wind relationship. So these are now the new data. So again, the Primavera 135 to 25, and these are the new data, 10 kilometers. You cannot see the ensemble members here, but believe me, there are 3 ensemble members here. So at 10 kilometers, we're starting to come closer and closer. And again, it looks good, but it's again the right result for the wrong reasons because we don't have an ocean. So if we were to go and look at the same exact result with a coupled ocean, it would probably look different. But just to say that this is like for like, we use the same SSTs and the same everything else. So definitely we are coming closer and closer and closer to the right intensity. The other thing is these are the PDFs in the observations for the wind and for the pressure, and the PDF looks really quite nice. There's quite a jump going quite close to, so the distribution of these winds and pressures looks very much like observations. So the model is trying to do the right thing, but again, we'll see what happens when we couple it to the ocean. Now, this is the, to me, more interesting result out of this study. What we are looking at here is the intensity. So this is a intensity based on pressure. And this is the latitude of maximum intensity. So this is just latitude. And this shows you the frequency that the maximum intensity will occur at a certain latitude. So what this is saying fundamentally is that at 100 kilometers, and I had seen it in I plot all the tracks one by one, these storms tend to develop slowly. They don't develop very much, so they go to in that case, well, category 1. But they develop in the extratropics. They don't develop where they should. So they're supposed to be tropical. They're tropical cyclones in terms of their structure, in terms of their morphology. But in terms of spending their lifetime in the tropics, they're not quite. They're going way too north. And then if you go to 60, this improves a bit. And if you go to 25, yes, it still improves. But still, they are living too much of their lifetime in the extratropics. And again, the latitude of maximum intensity is too much into the mid-latitudes. Now, 10 kilometers, this starts to change, I would say. There's quite a jump. So they spend more of their lifetime in the tropics. And also, you see, we have these much higher intensities. So this is closer and closer to what the observations say the tropical cyclone should look like. And these are the difference plots. So this is 3 of the ensemble members minus the 100, minus the 60, and minus the 25. So it's a systematic change as we go to 10 kilometers from all the other 3 coarser models. And so this is really important because in Huracan, we are trying to understand the risk of tropical cyclones in the extratropics. So if we use this model, basically there is no risk of tropical cyclones in the tropics, and there is a very high risk of tropical cyclones in the extratropics. It's not quite fit for purpose if we use that model. And you can, I hope I don't need to convince you that if you try to downscale that, you'll get the wrong answer. Yeah. So then, is it just a curiosity? Well, actually, we looked at the NextGEMS ICON and IFS models. So we are starting at above 10 kilometers and going down all the way to 2 kilometers. And we so these are the coarser and these are the finest resolution. We do see the same behavior in 2 more models. So ICON and IFS. So it's not just our model that does that. And that's very nice that we can reproduce that result in 2 more models. Now, the other thing here, I said before, I was suspicious of the things we were creating in the extratropics. And so I spent a bit of time now applying the cyclone phase space analysis to all the tropical cyclone tracks and distinguishing. So this is, again, the observations. This is what IBTrACS says are all the objects of interest in the IBTrACS data set. And this is what IBTrACS claims are the TS categories, so the sort of canonical tropical cyclones. And this here is the extratropical and subtropical phases of the lifetime. So the times when they're not quite canonical, they don't have that symmetry and they don't have that warm core structure. So they could be considered to be ex-hurricanes or something before things go into full canonical tropical cyclone morphology and behavior. And if I split now from the total data set, what the cyclone phase space tells me are canonical tropical cyclones and the rest, you can see that actually the agreement to observation, this is at 10 kilometers, but even at the quite coarse resolution, the agreement to observation is fairly good. So the regions where this happens are well reproduced. And we are now going actually from having too few to having about the right number, which in fact, if you noticed well, you can see it here. In a sense, we have possibly already too many, and then we have way too many, and then we come back down. So instead of ramping up the right number, we sort of go exaggerate and then come back. In so many ways, this has to do in the meta-office model with stochastic physics. We didn't have this before we introduced stochastic physics. In the meta-office model, it seems that stochastic physics is exciting too many of these things, particularly in the subtropics and extratropics. But in terms of canonical tropical cyclones, it seems that we still do the right thing. Now, in terms of, so let's say that 10 kilometers is currently the best model we have. So in terms of what we observe here, so these are the hybrid storms. So again, in terms of risk to North America and Europe, these are the ex-tropical cyclones. And this is a quite well-observed region. You could say they were still exaggerating, but it's not too far. And even in the Pacific, it's not too far. Where we strongly disagree is in the South Pacific and also in South America. And when we did the reanalysis paper with Kevin Hodges, this region was very much questioned by the reviewers. The reviewers said that we were dead wrong. There are not that many storms in that part of the world. And then Kevin went through the advisories from each agency and all that and found plenty of storms that were not in IBTrACS. So I would say possibly these two categories are not terribly well observed and the data are quite homogeneous. So I think we still need to research this quite a bit more and ask the agencies to be very careful about all this. But definitely this is the bit where the stochastic physics is, particularly in exotropics, generating far too much. And we need to be, again, very careful. If we go and use these coarser models for downscaling, we might get the right idea of risk, because for this set, and I suspect this happens in other models, stochastic physics is exaggerating. Now, just to say about that part of the world where forever we were told we're wrong, because the GCMs have been producing storms in this region for the last 20 or 30 years. So in IBTrack, so this is the official catalog, there is nothing. So they do have these ET and SS in other parts of the world, but they have zero in this area of South America. Our model, so this is all the storms. This is the canonical tropical cyclones, and these are the extratropical and subtropical. Produces that. Now, if you talk to my Brazilian colleagues, they have a number of papers, and so they've looked at different reanalysis. So ERA interim, ERA 5, and now they're looking at some easier simulations, and they find exactly that. So they don't just find it in EERIE, they find it in the reanalysis. And it turns out that the Brazilian Navy has a catalog similar to IBTrax, where they, every time that one of these happens, they describe it, they have a whole web page dedicated to each storm. They've already gone through the alphabet, they've restarted from letter A. So these things do exist, but if you listen to IBTrax, they don't. IBTrax doesn't contain such storms. And again, this is one example where models produce something that is of interest, that is severe. These things kill people. These are strong cyclones. And there's a bit too much worry about whether they are canonical or not canonical tropical cyclones, but they're very, very intense cyclones. So what we need to do is work with the Brazilian Navy and IBTrax and say, can you please put all this stuff in your catalog? Because if somebody is trying to tune their model, or if some of what these new machine learning people want to build a perfect model of tropical cyclones and they go to IBTrax, they will train it to do nothing because they think the data are saying that these things don't occur, and they do. And we did have a very severe one in 2004, Catarina, that happened there. Just a bit of a rant about machine learning, but just, again, that's where models are useful, to raise hypotheses, to challenge your observations, to try to understand the physics. And they are not canonical tropical cyclones, but the model does. I think it's remarkable that the model can do this, that the model can distinguish these different natures of the storms, these detailed morphologies of each storm, and then you put it together as a map, and it looks very much like observations. Particularly, this is the ones that people really pay attention to. I would claim that people pay a lot less attention to this. Right. So just to say that I've been trying to explain why we have this behavior with the more intense storms in the tropics. And one of the things I looked at is the storm size and this whole idea of beta drift, which depends on both storm size and storm intensity. And so there is a mechanism called the induced vortex dipole, which is basically a sophisticated version of beta drift. So in fact, if you look, this is what observations tell us. So the big and not so intense ones do migrate poleward in the observations, and the small and very intense ones stay in the tropics. And this is because of this phenomenon, induced vortex dipole. And so if you go through our resolution, so the coarses resolution, we basically just have this bit. And as we increase the resolution, so we're coming a bit closer to the observation. I wouldn't say it's a stellar agreement. I would say where it's going to. It's a bit like your plot panels in your paper about the models pointing all towards the observation. They're not quite perfect, but they're all pointing to observations. And this is what is happening as we go to 10 kilometers. The model is trying to produce small and intense storms that live in the tropics. And I think this is important. And again, we've looked at the NextGEMS models, so 25 all the way to 4 kilometers. And you can see as we go towards, and we even have 2 kilometer simulation we haven't analyzed yet, it starts to show the same behavior as the observations. So this is a powerful argument for using high resolution to simulate tropical cyclones in the climate system. Right. I said something about sub 10 kilometer. Many years ago, we had this exercise called Diamond. We took all the models out there that could go to some resolution around 3 kilometers. We were the coarse people at 5 kilometers. We ran a 40-day prediction, initialized cold. So no DA, nothing. At the time, the first one was just atmosphere, and then there were several others, and some were coupled. We're now moving towards Diamond 1 year. There is a whole experimental design that has been proposed for simulating the year 2020 for 1 whole year with these models. And we'll have a global hackathon in May of next year. Just to say, at the time we looked at the tropical cyclones in this set, so these are many models, including ours, and we looked again at the distribution of MSLPs and winds around the tropical cyclones. This is Falco Yute's paper, and they look pretty good. But this was only 40 days, and now we have an opportunity with many projects, including NextGEMS, to look at a lot more. The next question, so I've showed you a lot about intensity. The other question is intensification. We've seen in the last few years. So the first time I paid attention to this was in 2015. It was very late in the season. We had Patricia pummeling towards Mexico. There were very anomalous SSTs, and this thing developed into a horrible Category 5 storm in less than a day. And I was awake all night watching it in horror to see what it would do. And then we had Ian in 2022, and we had Otis in 2023. And then this year we had Beryl. I was on the news a lot with this one. Again, he developed very, very fast. And we had Milton again, and look, 5th most intense hurricane, 3rd fastest period of rapid intensification. So this is really important. I just showed you that intensity and track are related. So the other aspect is intensity, track, and the rate of intensification. So understanding where these things go has a lot to do with how rapidly they intensify. So Alex has actually looked at the NextGEMS simulations, and he's paid a lot of attention to the rapid intensification and also the tail of this distribution. There is a metric, this RI ratio. These are observations. He's looked at all these different models, and definitely in the lot. So this is the IFS coupled to FISM at 5 kilometers. There are some models that are coming very close to the correct rapid intensification. And again, here, there is another IFS coupled to FISM. This is a 4 kilometer IFS. It's coming very close. So again, he hasn't looked yet. These are all the development runs. They're about 5 years each. He hasn't looked yet at the production runs, which are 30 years each. But there is hope that eventually these GCMs might come fairly close to the correct rapid intensification. How am I doing for time? Am I okay? Yeah. Just to say, so all right, fine, very nice, all sorts of model details and this and that. Does it matter at all for climate change? So for a long time, we've been projecting tropical cycles into the future. So this is one of our efforts a long time ago from a PhD study in my group. So looking at the response to doubling and quadrupling CO2 with a coupled model. And then, yeah, for us, the most remarkable result was this reduction in the North Atlantic that we were projecting, and then other people showed it. And then, yes, in the synthesis of CMCC5 projections, you have notably some places where there is a reduction, and there's this dipole in the Pacific. But there is always this, the North Atlantic is tough. There is always this question about what the North Atlantic is going to do. And we upscale again 3 resolutions with, this is Malcolm's paper from the time. Again, this is not terribly different from what we found in these very idealized studies. So we have this dipole, so this polar shift, this reduction here. And you could say there is a reduction in the North Atlantic, similar to what we had with the previous generation models. This very much disagrees with, if we apply the GPI to the same model, so if you take the same exact run and we apply the GPI, you could say we see a polar shift here, which maybe is in agreement, but actually we see something else entirely in the North Atlantic. So this is really a difficult question. And then Susanna has been going on for a long time. This is from Susanna's recent paper. She's been saying, well, your models keep projecting this reduction in the North Atlantic, which is an El Nino response, but nature is doing the very opposite. So all the models are wrong. They're just going completely in the wrong direction. And we need to look at the Nino versus Nina distribution, and we need to understand why your models are not doing the right thing. Just to say that we've looked at this in these now production runs with the, this is the IFS at 9 kilometers and FISM at 5 kilometers. This is, for NextGEMS, this is the low resolution. And so we've looked at both genesis and track density, and this is again the difference. And we still see this polar shift in the Pacific, but we stubbornly, we see even at these resolutions, we see this reduction in North Atlantic. So either still these models cannot reproduce the relative frequency of El Nino and La Nina, or maybe in the future, this relationship is different. So maybe the models, so Susanna keeps saying, well, nature is going in this direction, but we are going, this is quite far into the future, and this is a very strong scenario. Maybe this is changing in these models, and it could be entirely, just to say that resolution is not solving this mystery at all. We still don't know why, and I don't think we should try to do this at these top resolutions. It's I mean, we could see the same thing at 90 kilometers many years ago, and maybe we need to understand more the mechanisms. But so yeah, this is still an open question. Okay, do I have time to talk about hurricane? I hope.
Yeah, okay.
Yes. So just to say, out of all this came this idea, well, we've seen quite a few things like Sandy and a few other storms going to really high latitudes. And we've had a few close calls, and the most famous one is probably Ophelia, which came very close to Ireland, nearly as a warm core tropical cyclone. And because these things are so expensive, and when they happen, and they also kill a lot of people, there was this idea of putting together a project between the UK and the US to look at the risk on both sides of the Atlantic. And this was very much motivated by Ryan Harsman's paper, where he says, well, potentially there are three things that are changing with climate change. Part of it is the genesis, so it has to do with the SSTs, but also this whole idea of something that is spawned at the wrong time in the season. And because of what the anticyclone is doing at these wrong times in the season, there is a chance that they might come up straight to Europe. And then this expansion of the mean development region, and again, it has to do with what is happening with both the SSTs and the circulation. And so the different routes that the storms can take to Europe. So the relative ratio of the ones that go through and the ones that go around and still come back to Europe. And then this whole business of the intensity and circulation. So maybe in the future, so this idea, I didn't show it, but in Knudsen's summary of what's going on, there is this idea that the stronger ones are increasing and the categories 1 to 3 are decreasing. So maybe if we have fewer but more intense tropical cyclones, they might survive longer, and they might eventually migrate into the mid-latitudes, survive higher wind shears and all that. And then they might undergo baroclinic re-intensification like Sandy did, and then cause damage. And so the whole idea is to understand how these things change, when do they go extratropical, and how do they interact with the jet? And what is the chance then that they might hit here or hit Europe? So this is what we proposed in 2021, and then 2022 came, and we had everything. Everything we said happened the very next season. So we had a fantastic set of, one generating here. We had all sorts of things like Ian generating and going to very high latitude. We had Fiona that made landfall in Canada. It was a serious one. Yeah, this one that generated at very, very high latitude and was moving towards us. Everything you can imagine just happened. So this is a really interesting problem. And yes, this is still based on Ryan Harsman's simulations. He had some of these in his simulations in 2013. But yeah, so 2022 already a fantastic year to study this problem. So we're throwing everything at it. So we are using a number of products from very coarse, but with lots and lots of storms, where we mostly study the environment of the, we call them cyclones of tropical origin, CTOs, to all the high resolution climate simulations we have, to seasonal predictions, which are very high resolution and very large ensembles, and these GSRMs, these storms at 10 kilometers or less. So we have very large sample sizes all the way to tiny sample sizes, but we can try and use all of these resolutions and complement these things. So this is an example of things. I've been looking at things that generate over Africa, 5 kilometers. There's plenty happening here. In this case, for this year, just about anything that develops over Africa, when it hits the sea, it fires off and becomes a very intense tropical cyclone. There are other years in which things develop here, come to the ocean and die. So this is an interesting year, and this is again the year we decided to use for the global hackathon. And yes, there are differences in studying this problem. If we use Tempest Extremes, which is the tracker of choice nowadays, because it can run online, we don't need to write all the data. We miss out most of these genesis over Africa. So this is a caveat of using a much more appealing tracker. So just to say, I think this is possibly the most interesting bit of the current analysis. Leo Saffing at Leeds, who works in Huracan, has been looking at these hindcasts, has been extracting interesting cases from the hindcasts, and he's been looking at things that generate, already are contained in the initial conditions, and things that generate spontaneously in the model. And then he split, so this is the total number of storms he's been looking at, and these are the different months. So many of them happen quite late. And then he's split the origin. So these are things that happen at very high latitudes in the middle of the Atlantic, and definitely these happen at the tail of the season, so November to December. And these happen more in the canonical season, the ones that comes off Africa. So what's interesting about these is because they are in the hindcast, they are quite intense, and also we have ensembles, so we can go and find what we consider to be physically plausible storms. So they're not observed storms, but they're physically plausible. And so we're building a huge database. And Leo has been looking at now, in this case, he's trying to figure out where the points of origins are for each month of all the possible candidates that end up. In this case, the gate is Europe. It's the same gate that was used by Sainsbury et al. For the reanalysis. And these are the ones that he categorizes in the same set as being extratropical cyclones. So quite different points of origin and quite different seasonality. The question now in all this is whether or not the cyclone phase space that we're using, so this is Bob Hart's cyclone phase space, is adequate for these storms. And he has examples that he showed this week where, in fact, if you listen to cyclone phase space, so he's looking at many new realizations of Ophelia. I forgot how many, 20 or 30 realizations of Ophelia. And CPS thinks the Ophelia has gone ET quite early on. But there's a new cyclone phase space analysis from Hannah Crode and John Methven that actually is much more suitable for something that is embedded in extratropical environments. And in fact, if you plot Ophelia and you plot the thermal structure of Ophelia, it definitely has a warm core. And the standard CPS, which is meant for the tropics, doesn't detect it, but the new CPS that was developed already is able to detect it. So this whole business of false positive, false negatives and all that is a big topic. So this separation of what is a canonical tropical cyclone, extratropical cyclone, will be revisited several times. We want to have two very clear data sets, and we want to find the point of extratropical transition very precisely. And I think it's really promising what they're doing. And again, this was a whole PhD on the detailed dynamics of these storms and their environment, which will translate into a new diagnostic. And I'll stop there just to say that, yes, a lot of worry about what is and what isn't a tropical cyclone. The reason, there is a paper by Alex Baker. The reason is, if you look at the intensity at landfall and you look at what the hazard is at landfall, if you look at Alex's paper, you will see that the main hazard at landfall is different depending on the nature of the storm. So we need to know whether they are canonical cold core, so the run-of-the-mill extratropical cyclone, or canonical warm core, which we still think might happen before hurricane ends. We'll see. And much of a hurricane is about making sure we have the impact model suitable for understanding the impact, especially storm surge. The storm surge we have in England is not suitable for warm core tropical cyclones. And then any hybrid. So if you look at Alex's paper, he will tell you that the hazard is different. So it means when we're studying the impacts, we need to pay attention to this. Anyway, out of all I said is in low resolution GCMs, I would say the current result that I find exciting is that they develop very much into the extratropics and they're very weak and too big. And at 10 kilometers and beyond, we start to have tropical cyclones that actually spend a lot of their lifetime in the tropics and are of the right intensity. And this does matter to understand the relative risk in the tropics and extratropics. I think this is important. So if you're going to downscale anything, I would suggest that we downscale everything you want to downscale with all those scenarios, but please can we also downscale this 10 kilometer and beyond, because these have very interesting relationships between the tropical cyclones and the large scale circulation. And I'll stop here so that we can have a bit of a challenge to what I said. Thank you.
So thank you for Luigi. Do we have any question in the room? Please stand up and speak loud because of the mic over there. Right, Manos?
Thank you very much, Luigi. My question is quite, let's say, simple one, but difficult perhaps to answer. Why, when we increase the resolution in the atmosphere, I will understand why we expect a better representation. But have you seen that also the oceanic resolution has a role, and how do we understand this role? Has it Does it have to do with seeding perhaps, or?
So yeah, this is so there is a whole work package in Huracan, and we put some of it in EERIE, which has to do with studying the seeds. So understanding where the jet is and understanding what happens to this, anything that comes out of Africa when it hits the ocean. So how deep is the mixed layer? What kind of energy will it be able to extract from the ocean? But there are some people and I asked them to send me a plot, but they said it's not quite ready. So there are many case studies of looking at an atmospheric eddy going over a region where there are ocean eddies and going over a region where there aren't, and looking at the fluxes and looking at whether that is different. So this is what people are generating in terms of composites. But it's quite clear to me that if you take all of these runs and you look, Benoit Vanier did a lot of these Hoff-Müller diagrams. There are situations in which these seeds come out of Africa, and the minute they hit the ocean, everything dies. So he calls it the hurricane desert. And there are other situations they hit the ocean and they explode. And so I was showing you one in which they explode, but that one, the particular one is atmospheric. Yeah. So this is one of those things that EERIE is doing. Yeah. Still early days. Maybe in a year's time, I'll have some plots.
Thank you very much.
Very interesting talk for somebody who knows a little about tropical cyclones like me. Very nice. I was wondering, you have shown results of resolution increasing exercises where the top resolution was maybe 25, 10 kilometers and so on. I assume that all those models have parameterization of deep convection. When you start showing sort of series of resolution increase experiments, when the resolution starts going 5 kilometers, 2 kilometers, or stuff like that, then you have a problem of parameterization of deep convection. And what you said about stochastic convection, stochastic physics in general, I think suggests very much that the parameterization of deep convection is not obviously crucial, is even more than obviously crucial in whatever you represent. Then what happens in those extremely high resolution experiments? Does one chop deep convection halfway through when the resolution goes below a certain threshold value, or how do you deal with that?
Yeah, so we use religion.
Belief.
So when we wrote NextGEMS, I was really worried that the reviewers were going to murder us on this thing, because basically Bjorn and Irina were suggesting we should do all the simulations with no convective parameterization. And I said, okay, but you're not at 1 kilometer, and even 1 kilometer will be enough, and you're coming very close at the other end to about 10 kilometers, and you're saying we're just switching it off, right? And then he said also typical Bjorn things. He's an old friend, it's okay. He said also some good things about this. And I agree with many of the things he said, but it turns out that eventually EC and the hit back and said, so sorry, we can't run our model without the convective parameterization, in part because the convective parameterization is sweeping up all sorts of instabilities. And yeah. So what they ended up doing in the end, after a few random walks, was to take the mass flux and to reduce it by a certain amount. So it's still running, but with reduced mass flux. In EERIE, you have a mix of approaches. We wrote as UK, so because we're using the Methodist model, we wrote that what we're going to investigate in EERIE is a new convective parameterization called COMORPH, which in the new incarnation, which is coming out now, has a scale awareness. So it's an experiment. Yeah. It's a whole new thing that they spent 8 or 10 years. These are Arakawa's ideas, and they try to implement those ideas. It's a completely new convention.
ECMWF also goes very much for scale aware parameterization.
So we put it in as a model development and a really experimental kind of thing to see what happens. I do know that in the COMORPH that Malcolm has now, which still doesn't have this scale awareness, like for like, his storms are closer to OBS, and even his interannual variability has gone a notch up. So something in that parameterization is responding to the environment in a more realistic way than the conventional convective parameterization. But yes, it's a horrible place to be. This is why I was so worried about proposing to run on 10 kilometers. That scale, if you keep it, is wrong. If you switch it off, is wrong. There is no good thing that could come out of it. You're still doing something very bad, right? And I can tell you that actually, because the new thing we're starting are NCASs as we go towards those scales. So at 10 kilometers, the NCAS is not particularly good. We have way too many and they're too weak. We have the right precip for the wrong reason. Now, if you switch off the deep convective parameterization, magically, we get the right number and they're much more intense. However, the tropical cycles look far worse. So we have a huge improvement in NCSs and a decay because it's a stupid resolution to run at. We shouldn't be at 10 kilometers. The reason we are at 10 kilometers is the ocean. That's why we're doing that. So yeah, that's a big issue. And NextGEMS is completely different because Icon is running entirely without, and the IFS is using reduced mass flux.
Thank you.
Any other question? I have a couple. Maybe did you also try, because you have shown that there is a huge role of the resolution in a better representation of the TCs in our models. And did you also investigate and quantify such a role in terms of relationship between the TC activity and the climate system? I mean, for instance, how better the higher resolution is in representing the relationship between the main modes of variability and TC activity in the different basins, etc.
So you're saying if we split it into all these AMOs and Enzo Plaza, Enzo Minors, yeah. So we had a whole thesis now on this by Penelope Lozo, who unfortunately finished the PhD and went back home to help her family through the COVID.
Oh.
So she wrote one of the papers, which is the last chapter on risk, and that's published as a book chapter. But the main one, which is to show how all these models do, she's now written, 3 years later, she's now written a paper, which is sitting on my desk for me to review. The models do surprisingly well, especially in the Atlantic multi-decadal modes. They're doing particularly well. I wouldn't say they're doing so well in ENSO. Okay, but the decadal modes look quite nice, quite realistic. So of course, I wish we had one. And that's why I'm excited that Malcolm is doing the simulation from 1850.
Yes.
Yeah, all the way to 2100, because maybe then we can look at that. But unfortunately, it's one model. But yeah, so she's done a lot of work on that.
But the other question I had, based on one of your first slides, I mean, you run several members starting from 1979, 10 kilometers. So my question is, what about the spin up? How did you manage the spin up?
So for the atmosphere only model, the ones I was showing were atmosphere only.
These are, you still didn't run any couple.
We have a few experiments. So we had one implementer and we have a few experimental ones, but it was just to look at model development. What I want to do is when Malcolm has arrived at 1950, I want to restart the system coupled from 1950 on at 10, because he's had to downgrade his model to 20 because his computer never arrived. So they're still waiting to start on a new computer. So I want to run, and I want to run an ensemble, yeah? But I still had to spin up the cryosphere, the soil moisture and all that. So what I did is I did a number of 5-year runs to bring the model to some sort of stable state. And then all of my initial conditions are perturbed from these spun up states for the cryosphere and the land surface. But yes, then the SSTs are the same.
Because I mean, you also said that you expect different results if you couple with the ocean because of the intensity, the SST feedback and whatever. And we have seen already in Primavera that 100-degree resolution ocean coupled with the atmosphere at the same resolution is sufficient to represent such a feedback. So my question is, to which extent, apart from the problem of the spin up, but I think that it is not that much a problem of computational cost, coupling the ocean at the 100-degree below your 10 kilometers.
I mean, the purpose of EERIE is not tropical cycles. The purpose of EERIE is to understand things like transports and particularly what's happening in Antarctica and all that. And there is also a bit about the implications for the CO2. So if we had a biogeochemistry model, what would be easy? Because You remember we had this massive error in the Southern Ocean. So the model at 40 degrees in many of the Primavera models is way too warm. The idea was that potentially we do away with that massive error, and that has implications for the carbon cycle. But my point about tropical cyclones, so tropical cyclones is a tiny bit of EERIE, really a tiny bit.
Okay.
But my point is, if it's true from what we've seen at NCAS and what we've seen in our own simulation, then the internal variability is larger. This might project onto these decadal modes of variability, and this might project onto the variability of tropical cyclones, and also the interbasin relationships. This might have an effect on all that, but we don't have the runs yet. So the runs are still in phase 1, which is the development runs, and many will try to start the production runs next year.
Okay.
So we're very late with all that, but we have been looking at the tropical cyclones, and we do have also because Malcolm is using a different, as I was saying, he's using comorph. So we have my set, which is continuing Primavera, many years after Primavera, but I want consistency. And then we jumped to a different model, and we are restarting everything. So Malcolm is also running 20 coupled, 20 atmosphere only, and then we have 10 atmosphere only, and we don't have yet 10 coupled.
Okay.
So, but if that is true, that might have massive implications on the variability, long-term variability of tropical cyclone, and on these interbasin relationships.
Okay.
Yeah.
So, yes, Silvio, go ahead.
My question is about one of the first slides that you showed. The one with the distribution of the tropical cyclone. That one, no? Distribution of
The pressure, yeah.
Here. You said that the French model has the right distribution for the wrong reason. Can you elaborate a bit?
So
Explain why it's the wrong reason and what? Because here the French model, if I got it right, is the one with the highest resolution.
no, all of them went to about 20 kilometers. Yes. So it's the one that has the strongest category in terms of wind speed. So normally what happens is that you have these, the Louis relationships, Louis 79, to get through the logarithmic wind profile, and you have these Louis corrections to go from, say, 925 down to sea level and find what the 10-meter wind is. It is possible to change these relationships, to change the profile, and so many of these models have about the right winds at 850 or even at 925. But when you descend into the surface layer, they don't have it. But if you look at what Chris Davis is saying, with these pressure gradients that we develop, it's unrealistic to form such strong winds at the surface. It's not to be expected. And so you can do it if you change the Louis relationships to allow the wind to come down from 925 unperturbed, basically. Okay. This is what we suspect they did. We've had lots and lots of conversations on how they achieved this. To me, it looks good, but although, it's a spectral model, so you got perfect gradients and all that, it's not diffusive and this and that. The equivalent resolution of spectral models is much higher than the equivalent resolution of finite difference models or finite volume models. Fine, with all those things, it's still a very suspicious result. Yeah. Yeah.
But that would justify the 10-meter wind, but not the minimum mean sea level pressure.
No, the mean sea level pressure, many models develop that. Some, even in prediction, some of these models develop to the pressures that they do.
Yeah, but in the following slide, you show the pattern with the mean sea level pressure.
Which these, yes. So I do have somewhere the MSLPs, yeah. But it is possible to develop very deep. So again, the gradient wind relationship is all over the place. The people play with all sorts of tuning this, tuning that, and also the size. There are too many degrees of freedom. But in many ways, I would say that as an ensemble of models at around 25 kilometers, the fact that we are coming close to OBS and not quite reaching OBS agrees with what Chris Davis is saying in terms of basic physics of the system.
Then if I may, maybe I have another.
Yeah.
question, which is about the result that you showed where you have the three distinction between you have the full cycle, the canonical, and not that one. Yeah, yes, this one. So, what is exactly how do you distinguish between the canonical? The canonical is the warm core, and the extra tropical cycles are the cool core.
No, so okay, so this is from Bob Hart's cycling phase space. So it's got four quadrants. So it depends on the symmetry of the storm and on the thermal structure. So you can have something that is warm and has a warm core and is symmetrical, but you can have something that is warm core and is asymmetrical. That could be a seclusion, for instance. You could be in the isotropics and have a seclusion. You still have a warm core, but it's not symmetric. Yeah. And then you can have the other bit, which is cold core asymmetric, and you could have cold core symmetric, and you could think of some very high latitude cycles of being perfectly symmetric. And so with Bob Hart's analysis, you can identify what in IB tracks end up being classified as these things, these extratropical and subtropical, because these have some of the characteristics. So they have a partial warm core, but they are not symmetric. And also they are not really deep enough and all that. So this is what we did in trying to separate what is really the proper warm core, symmetric, deep, and all that, which is the mid category, and what is basically anything else. Okay? And where they disagree is, of course, at high latitudes, both because Bob Hart's software is not designed for the environment of the astrotropics, and because I don't trust the observations in IB tracks to be. We know, for instance, that until the late 1990s, the National Hurricane Center was not paying any attention to anything beyond a certain longitude. Whenever the storm reaches some longitude, they dropped it. So if you plot a density of something, it's cut off because I say, oh yeah, it's there, we don't care anymore, poof, it's off. Now they're reconstructing, but we know for sure if you go to the 50s and all that, we have no information about what's going on beyond a certain longitude, yeah? If you look at much more recent periods when they started to pay attention and there's absolute continuity, then you can actually compare what the model is doing, because the model, again, it could be very much wrong, and I'm pretty sure it is wrong, but at least it's consistent. If it does it here, it also does it there. Yeah, it's the same physics.
Okay, and also the South Atlantic.
Yes, absolutely. So that one we do have help from the Brazilians. So I will try to initiate a sort of composite analysis based on those catalogs, because that's a proper observational set, and try to understand how deep the warm core is, and also how many are asymmetric, and this and that and that and that. So because they have what, 40 or something, we can try and do a few composites with those and use ours to compare.
So that moves to the next question, and we have to go in 5 minutes. From Anna Pirani, hi Luigi, thanks for the very good talk. I would like to understand better the interface between this simulation and understanding how TCs and extratropical cyclones will change with climate change. How will this be done? For instance, in terms of evaluation against the deck?
Well, we are tracking absolutely everything we do. So particularly what Malcolm is doing is as he runs the EERIE, everybody actually, as we run the EERIE simulations, the tracker called Tempest Extremes is running online and producing the tracks instantly, so that we don't. So this is part. So EERIE is trying to. So one of the objectives of EERIE is to increase the speed by a factor of 5 and decrease the energy usage of, I think, a factor of 3, which has been done before. So we know it can be done, and that uses stochastic physics, single precision arithmetic, very few diagnostics, and some parameterizations transformed to machine learning, and also machine learning used for data compression. So we're definitely, everything that we're doing, we're tracking with Tempest Extremes. The caveat is the thing I was saying before. We need to be very careful, because Tempest Extremes is very good at doing one storm. In this case, this is the version of Tempest Extremes that is calibrated to IB tracks. So it finds perfectly the IB tracks. but it's not very good at doing the early stages. You can see this is the same data set through our tracker and through temperature extremes. It misses all of these early stages. Yeah. So we need to be, and then there is another configuration of temperature extreme that finds the extratropical. So it's outputting all these things, but they are categorized, and that thing has been tuned to the current observations. So it will reproduce the current observations. What we want is this new cyclone phase space, which can adapt to a changing environment and is aware of what the background environment is, so that we have a much better classification of, okay, this one is a pure tropical cyclone, this one is a hybrid, this one is an extratropical cyclone. And then we can look at differences, all sorts of things like that.
Okay.
Yeah? So there is a huge effort here in running multiple trackers and also understanding how we use. So Stella keeps saying, don't say that track is better than temperature extremes, because we can build a workflow in temperature extremes that will do all that. But currently we still don't have it. And so currently we have to run bits and pieces and then stitch the tracks together to get a full data set. Yeah.
So this is somehow partially responding to the question by Leonardo. Maybe you can expand a bit on this. He's asking, Leonardo Regao, thank you for the engaging presentation. The increase in the resolution produces remarkable results regarding the intensity parameters of tropical cyclones. However, the literature shows that adapting the metrics using the detection method is necessary to achieve similar results in identifying cyclone, total number, etc. How was this adaptation made to identify tropical cyclone across different model resolutions?
It wasn't. So this is Kevin Walsh.
Yes.
He's big.
2017.
Yeah. So track first of all uses vorticity, it doesn't use pressure. And the other thing that we do is we bring all the data to a common spectral truncation to begin with. So it doesn't matter even when we run at 1 kilometer. So we even track the 1 kilometer, we bring it all to the same spectral truncation. And we identify on the same, so that we bring all the models to one spectral truncation. We put all the models there and we analyze them all together. So it's like for like. And then afterwards, we attribute things like surface wind speed, the pressure, the precipitation, anything you want, the temperature, whatever we attribute at the original resolution. But for tracking, we have one common grid and that's it. And there is no adaptation, because then if we, I've had an argument with Kevin Walsh. Huh? Yes, this is track. So temperature extremes is a bit different. The temperature extreme has a different set of variables and all that. And I have to say, it has been tuned to IB tracks. So they keep saying, they actually write in their papers, it's the best tracker. And I keep saying, okay. And Americans like to say that. Can you be a bit careful there? Because if you tune it so much for one product, and then you try to use it in 1850 or in the future, I'm not so sure, okay? And also, I say, it also depends on what you're trying to do, because if your interest is genesis, all the seeds and all that, it's laborious. So now Malcolm is running online. So if I now tell him, look, but I want to look at that, you told me before. So we can probably reconstruct, because we're still outputting, because we are paranoid, we're still outputting the data, but we have to redo it, okay? So, but the philosophy is different. I don't believe in this idea of adapting all our diagnostics to each resolution. In the same way, I don't believe in retuning the model at every resolution, because we're trying to understand what resolution does. We're not trying to run a beauty contest. I'm perfectly happy to show that, and we have, as Primavera, we've shown lots of things become worse with resolution. They become absolutely worse. And this is not a beauty contest. It's about understanding. And yeah.
Okay, so the last question, and then we close, still from Anna Pirani. The question is related to downscaling. You said at the end of your talk, please downscale the sub 10 kilometer runs.
Yes.
What do you mean by downscaling in this case? In relation to downscale the climate change simulation?
Downscaling anything that people do at 10 kilometer or less, take it and do a 50-member ensemble of that. Instead of taking, so this is what really, now I will go into a huge rant. Fasten your seatbelts. We have a project running here. We have a funded by a big Canadian foundation, whatever, called Pier. We have a project to look at this part of the world in terms of tropical cyclones. And so these people asked me to come in at the last minute, and of course I had already written what they were going to do, and I told them several times, this is wrong, don't do that. But in the end, they did it. What did they do? They want to study this region to understand particularly the risk of tropical cyclones in the channel. What did they do? They selected to study the risk of tropical cyclones here. They went off to the CMCC archive, and they selected the 5 GCMs that have the most diverse climate sensitivity. And I said, well, that is absolute rubbish. Those things have the circulation at completely the wrong latitude, and also again, some of them are so coarse they only have category 0.1. Yeah. So then you downscale that to convection permitting. So they go from that to convection permitting. So it's at the wrong latitude. The domains are tiny. What is the point? And then it's, oh yeah, there is nothing happening here. And of course, also because the boundary is on this side of Madagascar. And I was like, what? I said, can we please downscale my model that has a decent circuit? It's not perfect, but it's decent. And also you're starting from something that looks like a tropical cyclone with the right frequency and almost the right intensities. And then you take it to the convection permitting, you do 50 ensemble, but they want to look at rivers and all that, okay? But also, I have mountains. It's super important to get the cyclone through the mountains. In these IPCC GCMs, there are no mountains. The storm just pummels through, brings all the moisture from the other side of the, it's ridiculous. So they started, oh, but we need to have diversity in terms of the future warming. I said, but you're studying tropical cyclones. Fine, do that, but can we also downscale the models that have proper circulation? Sorry, big round. Because one of those in my PhD student.
I think that we can. There is another question in the room. Simon.
Sorry, then we will leave you to lunch.
You underestimate how much I have to talk.
It's just, it's just a little bit of curiosity to know your opinion about this. You mentioned several times based and methods and so on. So moving a little bit from climate to short-term forecast, there was an amazing article that came out New York Times at the end of July about everything. Well, I don't remember. Barry. Yeah, and they showed that actually the most skillful forms for this specific event, it was done with an AI-based model that actually was much more successful than the similar. So that it was just an event, an example. I mean, do you know of any?
No, we've seen the Pacific. So one of the people in my group works a lot in China across the Pacific. He keeps showing me such articles. People have done it many times. There are many situations in which these AI models do an amazing work.
So it's another example of good result.
Well, I don't know. So I don't know. I mean, these things are trained on realities. Okay, so they're trained on good data. And they also have the advantage they run 1,000 times the speed, right? So what worries me here is, and we've been accused several times of cherry picking, that we only show our good results, we never show our failures. So I'm a bit worried, if you have something that runs 1,000 times faster, you can run it, you can run an ensemble of 100,000 and you only show the 2 or 3 that are good. You don't show all the rubbish. So what is really good is ETN and Lab have their own AI model, which they run every day, and they also run 2 of the vendor models, and they compare, and they're actually showing that their own AI model is starting to beat these certain aspects. No, but it's really interesting for NWP. It's really interesting that we're doing this, but I think, and so in the program already, what we wrote, we have a fellowship program where we invite people who will come and solve the problem. We have grand challenges several years ago. We want them to still answer those. If they bring in AI, it's very welcome. But the focus is on an understanding. So, fine, you have this result. Can you tell us why? This is what I want. If you come to the fellowship and say, oh, look at this magic tool, it does great. I say, I'm sorry, I don't care about that. You can tell us why, so I know whether I can trust it, then fine. Okay? But if you just show me it's great, and you don't show me why, you're just a monkey, basically. You press some buttons, you get something out of it, and so I don't trust it.
Yeah, the question was, yeah.
So our
Regarding
proposition.
the why and regarding the statistics, that was just the depends on what it is, the body that is trying to move it up more.
If they were to perform, it's fantastic because we could have, and so I have an example from my Japanese colleagues who also run these resolutions, but they have, so one of the three challenges in writing is month-long prediction. So what they show is they run a 1,400 member ensemble for about a month. And when they run 1,400 members, they can actually differentiate two tracks in the Pacific, one of which is the typhoon the Hitman in 2019, very important typhoon. And the other cluster goes to China. They can really differentiate. And so they can actually say that they could have predicted the likelihood of something doing that to Japan 12 days ahead, which is amazing. But they have Fugaku, which is half an exaplot machine. If we could do something like that with AI, with a more common supercomputer, that would be amazing. You know, 1,000 something member ensemble for a month, and we have two clusters, one of which tells us that there is a likelihood of something coming to Japan. And they say if you only run 100, you don't see it. Okay. But we need to if it does it, we need to understand that we know why it does it, not that if this happened and next month you do it again and nothing. So of course, no use.
So regarding your slide about the separation between canonical disease and the sum of extratropical and tropical. So in the western Pacific, in the observation, there are two branches of extratropical cyclones and subtropical cyclones. Yeah, in the high structure. There's the one, I think it's extratropical one,
So this is. Yeah, so this is after the storms have undergone extratropical transition. So these are extratropical, but originally they were identified as tropical cyclones. Yeah, so this is the density of when we cut the track and say until now it was tropical and from now on it's extratropical. So that's that way. And these ones are the subtropical.
Yeah, my question was why does the model at 10 kilometer resolution is not showing the southern branch?
Oh, you're talking about the
Western
you're
Pacific,
saying it does this bit, but it doesn't do that bit.
yeah.
Yeah, so one of my Brazilian colleagues said the very same thing. I don't know why it could be they're too small or maybe too shallow. So we have something here. We have something here that I know is very shallow and we overestimate very strongly. And is often misclassified as a tropical cyclone. But here there is a little bit. But it could be the boundary layer is wrong. I don't know. My Brazilian colleague also noticed that. But maybe we need to go to the next resolution to see. I don't know.
I have a very last.
Oh, come on. It was okay. I think had her hand up.
Yeah, it's more than a question, it's more asking for speculation. First I have comments on the machine learning. I was going to ask something really similar because variable was actually well correctly forecasted both by the Google deep learning algorithm, this kind of fear everyone can run. So I totally this gentleman's exercise that you're doing it's absolutely only about understanding and not for short-term forecasting from the further or at least understanding how to improve the forecasting gas. But what they're doing with the machine learning algorithms, it's mainly exercise of one algorithm against the other, and the middle one was compared with the wrong one, but they are doing exactly the same. Of course, the effect is much more. But given the giant exercise that you're doing, and since all your models are global, just relating to the question that Hannes had on the at the Central Ocean, it's well known that they contribute a lot on the energy budget into that ocean and the North Sea terrains. So biased by the Arctic and polar region, there is any plan to look at the ocean and the Central Arctic, those resolutions are absolutely well resolved. The interaction with sea ice, I think that has some exercise in that, and the very nice atmosphere that we have.
So there are two groups, both in NextGEMS and EERIE.
Okay.
So in the picture, I put in EERIE as the sort of logo of EERIE is the polar region, the edges of the ice, and all the eddies that we see in those. So a lot of people are looking at this. So I have no time to show any of that, but I would say again, tropical cyclones for EERIE is almost inexistent. It's all about these interactions between the ocean and mostly the tropical storm path, but also these polar region problems, and claiming the south is this error in which these gigantic errors in the Southern Ocean. And then what the exchanges imply, particularly for, yes, of course, the heat exchange, but also for what are the indications that for at least the chemical part for this solution of CO2, we have 4 or 5 degrees error. That's not good for the other.
Yeah. The mic.
Sorry, I moved away.
Go ahead.
No, just so in the southern Atlantic, there are no what we call canonical cyclones.
That we know of. So this is always, yes, because
I mean, since that also the models that
Yes,
your
yes.
execution also the model
yes,
don't
but
want us to.
but the model started in 1979, so I'm not sure. If I were to run this thing since the 1800s, would it never ever do it? So we are also looking at hindcast. I think because of the ocean circulation there, and because of where these things originate, so a lot of these things actually originate to the lee of the Andes and then move out to the ocean and then develop. Okay, it is possible they might form a warm core, but they need to find a lot of energy, and also they need to find the right wind shear and all that. So in a sense, I mean, these are very short simulations, but from what we know, very recent times, they don't happen. It's possible that in a long time ago, maybe the latitude was different and the SSTs were different. Doubt, because there is a very strong current here that usually, if you go swimming here, it's quite cold actually. But I think it's fantastic that the models have been doing this for a long time, and now it comes out as a hybrid, and it absolutely doesn't come out as a canonical for this very short period. So the model is doing, in terms of physics, is doing a lot of right things. The chain of events, and certainly when we look at genesis and the directional propagation, they do form here and move out. We also see the same in this region. We see lots of things that form here and move out. It's not just stuff coming from the ocean. There are other things that form inland and move out to the channel, and the models can do that.
Okay, so we need to go. Thank you again, Luigi.
Thank you.